Something is happening on Mars. Not in the geological past, not in a theoretical model, not in the speculative margins of a scientific paper. Now. Something is happening on Mars right now, and the instruments we placed there, instruments designed by the most rigorous minds on Earth, built to detect exactly these kinds of anomalies, are sending back data that does not fit the models we have spent decades constructing. That alone should stop you. We are not a species that sends machines to other planets casually. Every rover, every lander, every orbiter humanity has placed in the vicinity of Mars represents billions of dollars, decades of engineering, and the collective intellectual labor of thousands of scientists across multiple generations. These are not amateur instruments. The sensors aboard NASA's Curiosity and Perseverance rovers are calibrated to detect chemical signatures at the level of parts per billion. The MAVEN orbiter has been mapping Mars's upper atmosphere since 2014. The Mars Reconnaissance Orbiter has photographed the Martian surface at resolutions sharp enough to distinguish an object roughly the size of a dining table from an altitude of 300 kilometers. We are watching Mars more carefully than any planet beyond Earth has ever been watched in the history of human civilization. And yet, there are readings coming from the Martian surface and subsurface that remain officially unexplained. Methane signals that appear and vanish on timescales that contradict every atmospheric model. Subsurface radar returns from the MARSIS instrument aboard the Mars Express spacecraft, suggesting the presence of liquid water, or something with the radar reflectivity of liquid water, buried beneath more than 1.5 kilometers of solid ice at the Martian South Pole. Oxygen fluctuations in the thin Martian atmosphere that spike and crash in patterns no known geochemical process can fully account for. These are not fringe observations from discredited sources. These are peer-reviewed, instrument-verified, published in Nature-level findings. And they remain open questions. The silence around some of these findings is not sinister. Science is not a press release. It is a process. But that process, when applied to a planet like Mars, produces a particular kind of tension. The tension of knowing that the data is real, that the instruments are functioning, and that the explanation is not yet in hand. Mars is not a mystery because we know nothing about it. Mars is a mystery precisely because we know so much. To understand why these anomalies matter, why a fluctuating methane reading on a cold desert planet 140 million miles from Earth can keep an atmospheric chemist awake at 3 a.m, you have to understand what Mars actually is. Not the cinematic version, the real one. Mars is the 4th planet from the Sun. Its average distance from Earth shifts dramatically depending on where both planets are in their respective orbits. At its closest approach, called opposition, Mars can be as near as 54.6 million kilometers. At its farthest, it retreats to over 400 million kilometers away. To put that in terms, the human nervous system can process a radio signal traveling at the speed of light, 300,000 kilometers per second, takes anywhere from 3 minutes to 22 minutes to cross that gap, depending on orbital geometry. There is no real-time communication with anything on Mars. Every command sent, every data packet received is a conversation with a significant delay built in. When something unexpected happens on the Martian surface, the scientists watching from Earth are always learning about it after the fact. The planet itself is approximately half the diameter of Earth. Its radius is roughly 3,390 kilometers, compared to Earth's 6,371. That size difference is deceptive, however, because Mars has no oceans. When you compare only the land surface area, the actual solid ground, Mars offers about the same total area as all of Earth's continents combined. It is an entire world of rock, dust, and frozen terrain, with weather systems, seasonal cycles, polar ice caps, and a geological history stretching back 4.5 billion years. That history is written in layers. The oldest Martian terrain, found in the southern highlands, dates to the Noachian period, roughly 4.1 to 3.7 billion years ago. During that era, Mars was almost certainly a different world. Mineralogical evidence gathered by orbiters and rovers has confirmed the widespread presence of phyllosilicates, clay minerals, in ancient Martian rock. Clay does not form in dry environments. It requires prolonged exposure to liquid water. The southern highlands are, in places, saturated with the chemical signature of a wet world. River-valley networks scar the oldest terrain. Enormous outflow channels, carved by catastrophic floods on a scale that dwarfs anything in Earth's recorded geological history, cut across the mid-latitudes. The largest of these channels, Case Vallis, is roughly 3,000 kilometers long and, at certain points, nearly 500 kilometers wide. A flood capable of carving that feature would have involved a volume of water comparable to the entire flow of the Amazon River, sustained not for days or weeks, but potentially for years. That world is gone. The Mars we observe today is dry, cold, and thin atmosphered. Its atmospheric pressure at the surface averages about 610 pascals, less than 1% of Earth's sea level pressure. For comparison, the atmospheric pressure on the summit of Mount Everest, the highest point on Earth's surface at roughly 8,849 meters, is about 33,000 pascals. The Martian surface pressure is about 50 times lower than even that extreme altitude. Standing on Mars without a pressurized suit, your blood would boil. Not from heat, the average surface temperature is around -60 degrees Celsius, but because at that pressure, the boiling point of water drops below body temperature. The physics are unforgiving. The transition from wet Mars to dry Mars is one of the most consequential planetary transformations in the history of the inner solar system, and it is not fully understood. The leading explanation involves the collapse of Mars's global magnetic field, which is thought to have shut down approximately 4 billion years ago as the planet's iron core cooled and solidified. Without that magnetic field, the solar wind, a continuous stream of charged particles flowing outward from the sun at speeds between 300 and 800 kilometers per second, began stripping away the Martian atmosphere directly. Molecule by molecule, over hundreds of millions of years, the atmosphere thinned. As it thinned, the greenhouse effect weakened. As the greenhouse effect weakened, temperatures dropped. As temperatures dropped, liquid water became unstable on the surface. The oceans, if they existed, either evaporated into a thinning sky or froze and eventually sublimated away. What remained was silence. 4 billion years of silence. A frozen, irradiated, chemically oxidized desert orbiting the sun in a state of apparent geological senescence. And then we started finding things that did not belong in that silence. The methane detections began drawing serious scientific attention in the early 2000s. Methane, chemical formula CH4, one carbon atom bonded to 4 hydrogen atoms, is an unstable molecule in the Martian atmosphere. Ultraviolet radiation from the sun destroys it relatively quickly. Scientists estimate that any methane present in the Martian atmosphere today should break down within approximately 300 to 600 years, which means that any methane detected right now was produced right now. It was not left over from ancient geology. Something, some process, somewhere on or beneath the Martian surface, is generating methane in the present day. On Earth, roughly 95% of atmospheric methane comes from biology. Microorganisms called methanogens, ancient simple life forms that thrive in oxygen-free environments, produce methane as a metabolic byproduct. They live in swamps, in the guts of livestock, in the deep sediments of ocean floors. They are among the oldest forms of life on Earth, belonging to the domain Archaea, organisms whose lineage predates the rise of oxygen in Earth's atmosphere by hundreds of millions of years. If a methanogen-like organism existed in the Martian subsurface, shielded from radiation by rock and ice, drawing on whatever chemical energy remained from ancient hydrothermal systems, it would produce exactly the kind of methane signal we are detecting. That is not a claim. That is not a conclusion. That is a possibility that the data cannot yet rule out. The other possibility, abiotic methane production through geological processes like serpentinization, where water interacts with iron and magnesium-rich rocks to produce hydrogen and, under certain conditions, methane, is equally real and equally under investigation. The honest answer is that we do not yet know which process is responsible. And the honest answer to the honest answer is that we are not sure we have the instruments on Mars right now capable of definitively settling the question. What we do have is a pattern. The methane concentrations detected by Curiosity's tunable laser spectrometer show a background level of roughly 0.4 parts per billion by volume, spiking occasionally to levels 10 times higher. The spikes appear to correlate tentatively with warmer seasons and warmer times of day, which would be consistent with a subsurface reservoir releasing gas as ice melts and pressure conditions change. The Trace Gas Orbiter, the European Space Agency spacecraft that entered Martian orbit in 2016, specifically to hunt for atmospheric trace gases with far greater sensitivity than any previous instrument, has so far failed to confirm the methane detections made by Curiosity from the surface. That discrepancy is itself a puzzle. Either the methane is being produced and destroyed faster than orbital instruments can catch it, or it is confined to a layer of the atmosphere too low for orbital sampling. Or there is something about the measurement methodologies that has not yet been reconciled. The data is real, the instruments are working, the explanation is not in hand. Somewhere beneath the rust-red plains of Gale Crater, something is exhaling. In June of 2018, the journal Science published a paper that stopped the planetary science community cold. Chris Webster and his team at NASA's Jet Propulsion Laboratory reported the results of 5 full Martian years of atmospheric sampling inside Gale Crater, conducted by the tunable laser spectrometer aboard the Curiosity rover. The mean background concentration of methane they measured was 0.41 parts per billion by volume. That number on its face sounds almost trivially small. 1 part per billion is equivalent to a single drop of ink dissolved in a standard backyard swimming pool. And yet that number, that near-invisible chemical whisper, carries implications that reverberate through every branch of planetary science, astrobiology, and our most fundamental questions about life in the solar system. Because the methane was not static. It breathed. Over the course of the measurement period, the methane concentration inside Gale Crater ranged from a low of approximately 0.24 parts per billion in winter to a high of 0.65 parts per billion in summer, a seasonal oscillation of roughly 60%. It rose when Mars warmed. It fell when Mars cooled. That rhythm, that repeatable seasonal pulse, is not the behavior of a random chemical contaminant. It is not instrument noise. It is not a one-time geological event. It is a cycle. Something on or beneath the Martian surface is responding to temperature and pressure changes in a way that causes methane to accumulate during warmer months and withdraw during colder ones. The pattern repeated across multiple Martian years. It was consistent. It was real. And then, on top of that quiet seasonal background, came the spikes. In late 2013, and continuing into early 2014, Curiosity's instruments detected a methane concentration roughly 10 times higher than the seasonal baseline, a sudden dramatic surge that appeared without warning and faded within a few months. Since that first event, the rover has recorded at least 6 additional spike events of comparable magnitude. These transient plumes do not follow the same seasonal pattern as the background signal. They appear unpredictably, they vanish quickly, and they represent a methane flux rate that, if extrapolated globally, would require a source of remarkable productivity somewhere on the planet. What makes this doubly confounding is the question of destruction. Methane in the Martian atmosphere does not persist indefinitely. Ultraviolet radiation from the sun, interacting with the thin Martian atmosphere, breaks methane molecules apart through a process of photochemical oxidation. The standard models of Martian atmospheric chemistry estimate that any given methane molecule introduced into the atmosphere should survive for approximately 300 to 600 Earth years before being destroyed. That is the expected atmospheric lifetime under normal photochemical conditions. But here is where the data becomes deeply uncomfortable. If methane is being produced continuously at Gale Crater, and possibly at other locations across the planet, and if its atmospheric lifetime is 300 years, then over centuries of accumulation, the total methane concentration in the Martian atmosphere should be detectable from orbit. It should be building up. It should be there, measurable, in the global atmospheric column. The European Space Agency's Trace Gas Orbiter, a spacecraft specifically engineered to hunt for trace atmospheric gases with sensitivity roughly 100 times greater than any previous orbital instrument, has been conducting this search since 2018. It has detected nothing. The TGO's two independent spectrometer systems, NOMAD and the Atmospheric Chemistry Suite, have established an upper detection limit for methane in the global Martian atmosphere that is more than 10 times lower than the lowest detection previously reported by Curiosity at the surface. This is not a marginal discrepancy. This is a fundamental, instrument-level contradiction between two independent measurement systems operating on the same planet at the same time. How do you reconcile a rover on the surface detecting methane with a spacecraft in orbit finding none? Three broad categories of explanation have emerged from the scientific community, and none of them is comfortable. The first is that the methane is real, produced near or beneath the surface, but destroyed so rapidly after entering the open atmosphere that orbital instruments never see it accumulate. Some researchers have proposed the existence of a surface photochemical destruction mechanism, perhaps involving perchlorates, chlorine-bearing salts that are abundant in Martian soil, that could break down methane far faster than standard photochemistry predicts. If methane is being destroyed in days or weeks rather than centuries, then a subsurface source could be continuously replenishing the local concentrations that Curiosity detects, while the global atmospheric inventory remains too low for TGO to see. That would mean something is producing methane on an ongoing basis, and something else is annihilating it almost immediately. Two unknown processes, operating in tandem, each one canceling the evidence for the other. The second explanation is more troubling from a scientific credibility standpoint. In 2025, a research group led by scientists at the Belgian Institute for Space Aeronomy published a reanalysis of the Curiosity methane dataset and identified a potential contamination issue inside the tunable laser spectrometer itself. The instrument has a small chamber, the 4-optics chamber, that sits adjacent to the cell where Martian air samples are held for analysis. Before Curiosity's launch, that chamber was inadvertently exposed to Earth's atmosphere, which contains methane at concentrations roughly 1,000 times higher than the sample cell. The contamination was identified early, and multiple attempts were made to purge the system before and during the mission. But according to the Belgian team's analysis, a tiny fraction of that residual terrestrial methane, less than 1,000th of the contaminated chamber's contents, could potentially diffuse across the seal, separating the two compartments and into the sample cell, producing a false positive detection indistinguishable from a real Martian signal. This finding has not closed the case. Other researchers have challenged the reanalysis, pointing out that the seasonal pattern of the detections, their repeatable correspondence with Martian summer temperatures, would be extraordinarily difficult to explain as an artifact of internal instrument contamination, which would not be expected to vary systematically with Martian seasons. An instrument leak driven by internal pressure differentials might vary, but matching the Martian seasonal calendar with this degree of consistency would require a coincidence of implausible proportions. The third explanation sits in the middle of the first two, and it is the one that most actively guides current field operations. The methane may be real, produced abiotically through geological water rock chemistry and concentrated in near-surface pockets, perhaps trapped beneath regolith or ice, from which it seeps out locally in quantities detectable at ground level, but too diffuse and too rapidly dispersed to register at orbital altitude. This is consistent with what we know about Martian geology. The planet's crust contains enormous quantities of olivine and pyroxene, iron and magnesium-rich silicate minerals that react with water through the process of serpentinization to produce hydrogen gas, which can then undergo further reactions with carbon-bearing compounds to generate methane. Serpentinization does not require biology. It does not require warmth. It occurs in cold, dark, anoxic environments, exactly the kind of environment that exists in the Martian subsurface. On Earth, the process drives entire ecosystems in the deep ocean floor, where communities of chemolithotrophic microorganisms, organisms that derive energy from chemical reactions rather than sunlight, thrive in the hydrogen and methane-rich fluids seeping from serpentinite rock systems. The Lost City hydrothermal field in the mid-Atlantic Ocean is one of the most dramatic examples. A forest of white carbonate towers, some rising 30 meters from the ocean floor, entirely sustained by the chemistry of water-meeting rock in the dark. No sunlight reaches it. No photosynthesis drives it. The energy source is purely geological. If an analogous system exists beneath the Martian surface, and the mineralogical evidence gives no reason to rule it out, then Mars may be geochemically far more active than its cold, silent surface suggests. The methane is just one line of evidence. The oxygen anomaly adds another. Over 3 full Martian years of atmospheric monitoring, Curiosity's sample analysis at Mars Instrument tracked the seasonal behavior of every major gas component in the thin Martian air above Gale Crater. Nitrogen and argon behaved exactly as expected, their relative concentrations rising and falling in lockstep with the seasonal condensation and sublimation of carbon dioxide at the poles. Oxygen did not. Instead of following the predicted seasonal model, oxygen concentrations rose by as much as 30% in spring and summer, then fell back to baseline levels in autumn. The pattern repeated each year. The magnitude of the variation changed year to year, but the seasonal structure did not. No known geochemical process, neither photochemical production from carbon dioxide, nor geological outgassing, nor any identified surface reaction, can account for this behavior. To be precise about what that means, the scientific teams responsible for this instrument, among the most experienced atmospheric chemists in the field of planetary science, have publicly stated that they do not have an explanation. The data has been verified. The seasonal oxygen enrichment is real, and it remains, as of the most recent published analyses, an open scientific question. Mars is producing gases, methane, oxygen, in quantities and patterns that its current atmospheric models cannot explain. The planet is not geologically dead. The silence of its surface is not the silence of inertia. It is the silence of a system whose interior processes are still unfolding, slowly, beneath kilometers of frozen regolith in the dark. And the methane is only the beginning of what the instruments have found. Beneath the south polar ice cap of Mars, buried under 1.5 kilometers of layered frozen terrain, the radar aboard the Mars Express spacecraft has returned a signal that points to something far more extraordinary, something that, if confirmed, would not merely reshape our understanding of Mars, but of planetary habitability across the entire solar system. The MARSIS instrument, Mars Advanced Radar for Subsurface and Ionosphere Sounding, is not a camera. It does not take pictures. It sends pulses of low-frequency radio waves downward through the Martian crust, waits for those pulses to reflect off subsurface boundaries between materials of different densities and electrical properties, then records the timing and intensity of the return signals. The physics is the same principle used in ground-penetrating radar surveys on Earth, scaled up to planetary dimensions and operated from an orbit roughly 800 kilometers above the surface. Each radar pulse travels at the speed of light, penetrates kilometers of rock and ice, and returns a reflected echo whose character encodes information about what lies beneath. In 2018, Roberto Orossi of the Italian National Institute of Astrophysics and his collaborators published an analysis of 29 MARSIS observation passes over a single target zone in the Planum Australe region of Mars, the broad, flat plateau that sits atop the south polar layered deposits. The analysis focused on a region roughly 200 kilometers wide. In that region, buried beneath 1.5 kilometers of layered polar ice, the radar returned an anomalously bright reflection. Bright, in radar terminology, means high radar reflectivity. High radar reflectivity, in this geological context, means the presence of a material that conducts electricity far better than ice or rock. On Earth, the material that produces exactly this kind of bright basal radar return beneath polar ice sheets is liquid water. The Antarctic ice sheet sits atop more than 400 subglacial lakes. The largest of them, Lake Vostok, is buried beneath approximately 4 kilometers of ice, has a surface area comparable to Lake Ontario, and has been isolated from the atmosphere for somewhere between 15 and 25 million years. We know these lakes exist not because anyone has drilled into most of them, but because radar sounding from aircraft and satellites reveals the same bright basal reflections that MARSIS detected at the Martian South Pole. The physical signature is unambiguous on Earth. Applied to Mars, the Orossi team concluded that the most consistent interpretation of their data was the presence of a subglacial liquid water body, a lake, roughly 20 kilometers across, trapped beneath the ice by a combination of geothermal heat from below and the pressure-suppressed freezing point of water enriched with dissolved salts. That last detail matters enormously. Pure liquid water cannot exist at the base of the Martian South Polar Cap under current conditions. The temperature at that depth is estimated at approximately minus 68 degrees Celsius, far below the 0-degree freezing point of pure water at standard pressure. But water is not always pure. On Earth, the subglacial lakes of Antarctica persist in part because dissolved minerals, salts leached from the bedrock over geological time, lower the freezing point of the water significantly, a process called freezing point depression. The same principle governs the use of road salt in winter. A sufficiently concentrated brine solution remains liquid at temperatures that would freeze pure water solid. Mars has salt, enormous quantities of it. Perchlorate salts, sulfates, chlorides. These compounds have been detected in Martian soil and rock by virtually every surface mission since the Viking landers in 1976. If those salts have been dissolving into water at the base of the South Polar ice sheet over billions of years, the resulting brine could remain liquid at temperatures far below the normal freezing point of water. Laboratory experiments have demonstrated that calcium perchlorate brines, one of the salt species abundant in Martian soil, can remain liquid down to approximately minus 74 degrees Celsius. That is cold enough to sustain liquid water at the estimated basal temperature of the Martian South Polar Cap. The implications cascade outward from that single measurement in ways that are difficult to overstate. Liquid water is not merely a curiosity in planetary science. It is the single most critical requirement in every definition of habitability that science has so far constructed. Every form of life known to exist on Earth requires liquid water for at least some phase of its biology. Not ice, not water vapor. Liquid water, with its extraordinary capacity to dissolve compounds, transport nutrients, and mediate the chemical reactions that underpin metabolism. The discovery of a potential liquid water body beneath the Martian South Pole, regardless of whether it is inhabited, means that the chemical and physical prerequisites for life as we know it may exist on Mars right now, in the present day, not merely in the distant wet past. But the story of this discovery did not end with the 2018 paper. Science rarely closes a case on a single data set. Subsequent analyses of the Marsis data by independent research groups produced a more complicated picture. A study published in 2022 by Aditya Kuller and Jeffrey Plout at the Jet Propulsion Laboratory examined a broader data set of Marsis observations and found that the bright basal reflections were not confined to the originally reported location. They appeared across a much wider area of the South Polar layered deposits, in places where the ice is thinner and where the geothermal heat flux would almost certainly be insufficient to melt ice into liquid water, even with the most aggressive salt depression scenarios. Liquid water cannot exist where the physics forbid it, regardless of what the radar says. This led to the alternative hypothesis. The bright radar returns might not be caused by liquid water at all. Instead, they could be produced by a layer of conductive material. Perhaps a deposit of hydrated silica, iron oxide minerals, or a specific type of frozen carbon dioxide ice known to have anomalously high radar reflectivity under certain temperature conditions. Basal sediments saturated with perchlorate salts, but frozen solid might also mimic the radar signature of liquid water if their dielectric properties fall within the right range. Each of these alternatives is physically plausible. Each is consistent with some portion of the available data. None of them is as immediately arresting as a subglacial lake. But science is not obligated to produce arresting conclusions on human timescales. To distinguish between liquid water and these alternative explanations, researchers need either a different type of observation, seismic data from surface sensors, heat flow measurements from deep probes, or direct sampling, or a dramatic expansion of the existing radar dataset with higher resolution instruments. The RIMFAX ground-penetrating radar aboard the Perseverance rover is conducting subsurface sounding in Jezero crater in the northern hemisphere, but it operates at depths of only a few meters to tens of meters, far too shallow to probe the deep polar stratigraphy. The ExoMars Rosalind Franklin rover, designed to drill up to 2 meters into the Martian subsurface in search of biosignatures, has faced repeated mission delays and has not yet reached Mars. The deep South Polar subsurface remains unreachable by any instrument currently operating on the planet. What Marsus has given us, then, is a question formulated in the language of physics, a radar echo with specific characteristics that we currently lack the tools to answer definitively. That is not a failure of science. It is science at its most honest and most demanding. The data constrains what is possible. It cannot yet dictate what is true. The chemistry of the Martian subsurface adds additional layers to this constraint. Any liquid water body beneath the South Polar ice, whether lake or saturated brine sediment, would exist in one of the most chemically extreme environments imaginable. The perchlorates that keep it liquid are also powerfully oxidizing agents. Perchlorate ions, when energized by radiation or heat, release oxygen violently. On Earth, perchlorates in soil are environmental contaminants toxic to most organisms because they interfere with iodine uptake and thyroid function. In concentrated, cold, dark brines, they create a chemical environment that most Earth organisms would find lethal. Most, not all. The microbial biosphere of Earth has repeatedly demonstrated an ability to colonize environments that appear, by surface world standards, utterly uninhabitable. The Don Juan Pond in Antarctica's Wright Valley is a hypersaline calcium chloride-dominated brine lake that remains liquid at temperatures as low as -50 degrees Celsius. It is one of the most hostile aquatic environments on Earth's surface, yet microbial life has been detected in its surrounding soils and, in some analyses, within the brine itself. The deep subsurface basalt aquifers of South Africa, more than 3 kilometers below the surface, harbor microbial communities sustained entirely by the slow chemical reaction of water with ancient rock. No sunlight, no surface chemistry, no connection to the biosphere above. These organisms have been effectively isolated for millions of years. They live in the dark, in the cold, drawing energy from hydrogen released by the same serpentinization reactions proposed for the Martian subsurface. The parallel is not proof of anything on Mars. It is a demonstration that chemistry does not automatically preclude biology. The boundary conditions that Mars presents, high salinity, low temperature, chemical oxidation, radiation at the surface, are conditions that Earth's microbial biosphere has already solved, in different combinations, in different settings, across billions of years of evolutionary experimentation. The question of whether Mars ever had the time and the conditions to embark on its own experiment in chemistry to life is inseparable from the question of when Mars lost its surface water, and how completely. The timeline of Martian habitability is not a simple arc from wet to dry. It is a more complex, contested, and scientifically active debate than most public coverage of Mars suggests. The Noachian period ended approximately 3.7 billion years ago. The transition to the Hesperian period, marked by widespread volcanic activity and continued but diminishing liquid water, lasted until roughly 3 billion years before the present. During the Hesperian, Mars was not yet a desert. Enormous volcanic outgassing events, particularly from the Tharsis volcanic province, a highland plateau roughly 5,000 kilometers across, home to the 4 largest volcanoes in the solar system, pumped enormous quantities of sulfur dioxide, water vapor, and carbon dioxide into the atmosphere. These eruptions, some of the largest in the inner solar system's history, temporarily thickened the Martian atmosphere and may have sustained transient periods of liquid water stability at the surface. Olympus Mons, the largest of the Tharsis volcanoes, rises 21 kilometers above the Martian mean surface level, 2.5 times the height of Mount Everest above sea level. Its base is approximately 600 kilometers in diameter. Setting Olympus Mons on top of the continental United States, its base would stretch from Washington, D.C. to Kansas City. Its caldera complex at the summit, the collapsed magma chamber at its peak, is 80 kilometers wide and 3 kilometers deep. This is not metaphor or exaggeration. These are the measured dimensions of a real geological structure on a planet that is, supposedly, geologically quiet. The most recent confirmed volcanic activity on Mars dates to within the last few million years, geologically recent by planetary standards. Some researchers have proposed, based on analysis of surface feature morphology and crater counting statistics, that small volcanic eruptions may have occurred within the last 50,000 years. If Mars is still volcanically active, even intermittently, even modestly, then the geothermal heat required to maintain a subglacial liquid water system at the South Pole becomes not just theoretically possible, but physically grounded in the planet's documented geological behavior. The internal structure of Mars, though imperfectly known, has been substantially illuminated by the InSight lander, which touched down in Elysium Planitia in November 2018 and operated until December 2022. InSight carried a seismometer, the seismic experiment for interior structure, that detected more than 1,300 Marsquakes during its 4-year operational period. The analysis of seismic wave propagation through the Martian interior has revealed a crust averaging between 24 and 72 kilometers thick depending on location, a mantle extending to a depth of roughly 1,400 to 1,600 kilometers, and a liquid outer core with a radius of approximately 1,800 kilometers, larger than pre-mission models had predicted. A liquid core means ongoing internal heat. It means Mars is not dead inside. The planet retains enough thermal energy from its formation and from the radioactive decay of elements in its interior to sustain geological processes, including, potentially, localized geothermal heating of the base of the South Polar ice. The radar anomaly, the methane, the oxygen fluctuations, the liquid core, the recent volcanism. These are not isolated data points. They form a coherent, if incomplete, portrait of a planet far more internally and chemically dynamic than the cold, silent surface would suggest. And somewhere in the orbital archive of Marsis, in data collected over more than 15 years of low-frequency radio pulses bouncing off the Martian crust, there are additional observations that have not yet been fully analyzed. The dataset grows every time Mars Express passes overhead. The answer to the liquid water question may already exist in the instrument's memory banks, waiting for the right analysis to surface it. The subsurface of Mars holds its secrets under pressure, under ice, and under silence. But the instruments are listening, and what they hear next may change everything. In August of 2024, a paper published in the journal Nature Astronomy by a team led by geophysicist Vashon Wright at the Scripps Institution of Oceanography delivered a finding that reframed every prior conversation about water on Mars. The team had gone back to the seismic archive of NASA's InSight lander, the same dataset that had already revealed Mars's liquid outer core and crustal thickness, and applied a new analytical approach to signals recorded during Marsquakes in 2021 and 2022. What they found was not at the surface, not at the poles, and not limited to a 20-kilometer patch beneath 1.5 kilometers of ice. The seismic waves were slowing down at depth. Specifically, in a layer of the Martian crust between approximately 5.4 and 8 kilometers below the surface, seismic P waves and S waves were propagating at velocities inconsistent with dry rock. On Earth, seismic waves slow detectably when they pass through fluid-saturated porous rock. The same principle used in hydrocarbon exploration, where geophysicists probe the subsurface for oil and gas reservoirs by analyzing the velocity anomalies in seismic return data. The Wright team's interpretation of the Martian velocity anomaly was that the pore spaces in a layer of mid-crustal rock, somewhere between 5 and 8 kilometers down, are filled not with gas, not with ice, but with liquid water. The volume implied by that interpretation is staggering. If the fluid-saturated layer extends globally, or even across a significant fraction of the planet, the total water inventory it represents could be enough to flood the entire surface of Mars to a depth of between 500 and 700 meters. Some estimates, applying different assumptions about porosity and layer extent, push that figure to between 1 and 2 kilometers of equivalent global ocean depth. To calibrate that number against something tangible, the average depth of the Arctic Ocean is approximately 1,000 meters. The hidden water reservoir implied by the InSight seismic data could, in volume, rival the Arctic Ocean. Buried in rock, in the dark, 5 kilometers beneath a planet whose surface temperature averages negative 60 degrees Celsius. This is not the Mars anyone modeled 30 years ago. The discovery reframes the question of Mars's missing water in a way that is both scientifically profound and geologically logical. The planet's early history included abundant surface water, rivers, lakes, and possibly a shallow northern ocean covering perhaps a third of the planet's surface during the Noachian period. As the atmosphere thinned and surface temperatures dropped, planetary scientists had long assumed that most of this water was lost to space through atmospheric escape, with the remainder locked into polar ice caps and hydrated minerals in the crust. The water budget never quite balanced. Isotopic measurements of hydrogen in the Martian atmosphere, comparing the ratio of deuterium, heavy hydrogen, to standard hydrogen, indicated that Mars had lost an enormous quantity of water to space over geological time, but the loss rates, when modeled carefully, left a significant fraction of the original water inventory unaccounted for. The mid-crustal liquid reservoir resolves that discrepancy. The water did not all escape. A substantial portion of it percolated downward through permeable surface rock over billions of years, descending to depths where geothermal heat from the planet's interior prevents it from freezing, where pressure from the overlying kilometers of crust keeps it in liquid form, and where it has been sitting, largely isolated, ever since. The parallel to Earth's own deep groundwater systems is direct and illuminating. Earth's continental crust contains vast quantities of deep saline groundwater stored in porous and fractured rock at depths far below any active hydrological cycle. Some of this water, called connate water or formation water in geology, has been trapped in rock formations for hundreds of millions of years, isolated from the surface biosphere, chemically distinct from modern ocean or freshwater, and yet in some locations actively hosting microbial communities that draw energy from the rock chemistry around them. The Witwatersrand Basin of South Africa, where some of the world's deepest gold mines descend more than 3 kilometers into ancient Precambrian rock, contains fracture water that has been dated to between 1 and 2.6 billion years old. Microbial life exists in it, not hypothetically. Confirmed, cultured, metabolically characterized microbial life, living at 3 kilometers depth in water older than the first complex cells on Earth's surface. If Mars retains a globally distributed liquid water reservoir at 5 to 8 kilometers depth, warmed from below by residual geothermal heat, insulated from the frozen surface by kilometers of crustal rock, potentially chemically enriched by billions of years of water-rock interaction, then the habitability argument for the Martian deep subsurface is not speculative. It is grounded in the demonstrated biology of Earth's own deep rock systems. The seismic evidence did not stand alone for long. In November of 2025, researchers at New York University Abu Dhabi published findings in the Journal of Geophysical Research. Planets showing that ancient sand dunes inside Gale Crater, the same crater Curiosity has been exploring since 2012, had been lithified, turned from loose sediment into solid rock by interaction with groundwater billions of years after the crater's surface lakes had dried up. The minerals responsible for cementing those dunes include sulfates and silicates, whose formation requires sustained contact with liquid water percolating upward from below. The surface of Gale Crater had been wet not once, but twice. First when surface lakes filled it during the Noachian, and again later when deep groundwater continued to move through the subsurface long after the surface had become arid. That second pulse of aqueous activity is scientifically critical. It means the transition from habitable Mars to uninhabitable Mars was not a single abrupt planetary death. It was a drawn-out process, measured in hundreds of millions of years, during which liquid water continued to exist, underground, in protected pockets, shielded from radiation and temperature extremes, long after the surface became hostile. Life, if it ever arose on Mars, would have had not one window of opportunity, but a prolonged sequence of retreating refugia, each one smaller and deeper than the last, each one a potential holdout where chemistry could persist. The recurring slope lineae, RSL, added yet another dimension to this portrait of a geologically and hydrologically active Mars, though their interpretation has proven more contentious. First identified in Mars Reconnaissance Orbiter images in 2011, RSL are dark, narrow streaks, roughly 5 meters wide and up to several hundred meters long, that appear on steep slopes during warm Martian seasons and fade during cold ones. Their seasonally recurring behavior, their association with warm temperatures, and spectroscopic detections of hydrated salts along some of them prompted initial interpretations that they represented briny liquid water seeping intermittently to the surface. NASA held a press conference in September 2015 to announce that the findings constituted the strongest evidence yet for contemporary liquid water flow on the Martian surface. The scientific community's confidence in that interpretation has since diminished considerably. Subsequent high-resolution imaging and analysis suggested that many RSL occur on slopes too steep to retain any water-bearing sediment, and that their characteristics are more consistent with dry granular flows. essentially very thin avalanches of dust and sand triggered by seasonal temperature changes, then with liquid seepage. A 2017 reanalysis by Colin Dundas and colleagues at the United States Geological Survey concluded that dry, granular processes explained the RSL morphology more parsimoniously than liquid water. The hydrated salt detections were real, but those salts may be drawing water vapor from the atmosphere through deliquescence, absorbing moisture without ever forming a flowing liquid. This episode in Mars Science is worth dwelling on. A finding announced by NASA with considerable confidence was substantially revised within 2 years. That revision did not represent a failure of science. It represented science functioning exactly as designed. New data constraining and correcting prior interpretations, the process self-correcting through peer review and continued observation. The lesson it carries for the methane detections, the Marsis radar anomalies, and the InSight seismic results is straightforward. Extraordinary findings require sustained scrutiny, and the history of Mars exploration is littered with interpretations that required revision as more data arrived. What survives that scrutiny, what remains standing after repeated attempts at alternative explanation, carries correspondingly greater evidential weight. What has survived and what the seismic data from InSight has substantially strengthened is the conclusion that Mars retains liquid water in its deep subsurface right now. The evidence from Wright's 2024 analysis was independently revisited in early 2025 by Ikuo Katayama at Hiroshima University and Yuya Akamatsu, who applied laboratory measurements of seismic wave behavior in wet versus dry diabase rock, a basaltic rock type that serves as a close terrestrial analog to Martian crust, to the InSight dataset. Their results, published in the journal Geology, confirmed the velocity anomalies in the 5 to 12 kilometer depth range and strengthened the interpretation of fluid-saturated porous rock. Two independent teams, using different methodological approaches, arriving at the same conclusion from the same dataset. The convergence of evidence is no longer subtle. Seismic anomalies pointing to deep liquid water. Radar reflections at the South Pole consistent with a subglacial brine body, methane cycling seasonally in the atmosphere above Gale Crater. Oxygen fluctuating in patterns no known chemistry can explain. Groundwater continuing to move through the shallow crust billions of years after the surface dried. A liquid iron core still generating internal heat. A geological history of volcanism extending into geologically recent time. Each of these findings, taken alone, admits alternative explanations. Taken together, they describe a planet whose interior and subsurface are not passive and frozen, but active, chemically complex, and, in the specific, technical, astrobiological sense of the word, potentially habitable. The word potentially carries enormous freight. It is not a claim of life, it is a statement about conditions. Habitability is a necessary condition for life, not a sufficient one. Mars may be habitable in its deep subsurface and entirely lifeless. That outcome is scientifically possible, and perhaps even probable, given how little we understand about the origin of life even on Earth, where we know it succeeded. But the instruments have now established, beyond reasonable scientific doubt, that the physical prerequisites for life as we understand it exist on Mars in the present day. That changes the question. Not whether Mars could have supported life in the past, whether Mars could support life now. And the answer, constrained by the best data humanity has yet produced about another world, is one that no planetary scientist in 1976, when Vikings biology experiments returned ambiguous results from the Martian surface and were largely set aside, could have predicted with confidence. The answer is, we genuinely do not know. And the not knowing is no longer the not knowing of ignorance. It is the not knowing of a scientific community standing at the threshold of a measurement that has not yet been made, a drill that has not yet gone deep enough, a seismometer that listened for 4 years and gave us the shape of the question without yet delivering the answer. The next instrument, the next mission, the next dataset may carry within it the most consequential finding in the history of science. Or it may not. That is what makes it science. The deepest hole ever drilled into the Earth's surface is located on the Kola Peninsula in northwestern Russia. The Kola Superdeep Borehole, begun in 1970 and drilled over the course of 24 years by Soviet and then Russian scientists, reached a final depth of 12,262 meters, just over 12 kilometers, before thermal conditions made further drilling impossible. At that depth, the temperature of the surrounding rock had climbed to approximately 180 degrees Celsius, far hotter than the models had predicted. The rock was behaving like a plastic rather than a brittle solid. The drill could go no further. 12 kilometers. After 2.5 decades of continuous effort, using the most advanced drilling technology available to one of the most technologically capable states in human history, we reached 12 kilometers into our own planet. The liquid water reservoir implied by the InSight seismic data on Mars begins at approximately 11.5 kilometers below the Martian surface. The bottom of the water-bearing layer extends to roughly 20 kilometers depth. The Kola borehole, humanity's deepest physical penetration of any planetary crust, would reach just barely to the top of the Martian aquifer. If it could be transplanted to Mars, if Mars were not a different planet with a different gravity and a different crustal composition, and if the technological infrastructure required to drill on another world had already been built. None of those conditions are currently met. The water is there, encoded in the behavior of seismic waves. It is as unreachable today as the bottom of the ocean was to the ancient Greeks. That inaccessibility is not merely an engineering frustration. It is a scientific statement of the highest order. The data tells us something exists. It tells us approximately where it is. It tells us approximately how much of it there may be. And then it stops. The instruments we can afford to send, with the technology we currently possess, cannot go further. We are reading the shadow of an ocean on the wall of a cave, and the ocean itself remains in the dark. The volume estimates drawn from the seismic velocity anomalies and the porosity models applied to Martian mid-crustal rock suggest a water inventory that would produce a global ocean between 500 and 2,000 meters deep if spread across the entire Martian surface. The uncertainty in that range is itself informative. It reflects genuine unknowns about the porosity of the rock layer, its lateral extent, and the fraction of pore space actually saturated with liquid versus partially filled with ice or gas. The lower end of the estimate is roughly equivalent to the volume of water locked in the Antarctic ice sheet. The upper end approaches the volume of the Arctic Ocean. Either figure, if confirmed, would represent the largest known reservoir of liquid water in the solar system beyond Earth's oceans. That statement requires a moment's pause. Europa, the moon of Jupiter, is widely regarded as the most promising candidate for extraterrestrial liquid water in the solar system. Its global subsurface ocean, maintained by tidal flexing from Jupiter's immense gravitational field, is estimated to contain between 2 and 3 times the total volume of all of Earth's surface water combined. Europa almost certainly has more liquid water than Mars. But Europa is 628 million kilometers from Earth at its closest approach, more than 4 times the distance to Mars. Sending a probe to drill through Europa's ice shell, estimated to be between 10 and 30 kilometers thick, and sample the ocean beneath represents a mission of staggering complexity that humanity has not yet come close to executing. Mars is closer. Mars has been visited by more spacecraft than any other planet. Mars currently hosts multiple operating rovers, orbiters, and landers. The infrastructure of scientific presence at Mars, the communications networks, the orbital mapping databases, the surface geology surveys, is more mature than for any other body in the solar system beyond Earth and the Moon. If liquid water exists in the Martian mid-crust at depths between 11 and 20 kilometers, Mars may represent the most accessible large liquid water reservoir beyond Earth, even accounting for the drilling challenges. Accessible is a relative term. Drilling 20 kilometers into the Martian crust exceeds current capability by more than an order of magnitude. The deepest borehole on the Moon, drilled by the Apollo 17 astronauts, reached 3 meters. The deepest borehole on Mars, attempted by InSight's heat probe, the HP-3 instrument, designed to hammer itself 5 meters into the regolith to measure heat flow, never fully penetrated the surface due to unexpectedly cohesive soil behavior and was officially abandoned in January 2021. Mars resisted even that modest intrusion. The gap between where we can drill and where the water is represents one of the defining technological challenges of 21st century planetary exploration. Bridging it will require not incremental improvements to existing technology, but fundamental advances in autonomous drilling systems, power generation on the Martian surface, and drill bit materials capable of surviving 20 kilometers of thermal and mechanical stress in an environment where logistic support is a radio signal traveling at the speed of light. And yet the motivation to bridge that gap is stronger than it has ever been, precisely because of what the water's presence implies about biology. At the temperatures and pressures that exist at 10 to 20 kilometers depth in the Martian crust, geothermal heat from the planet's still warm interior creates conditions that, on Earth, host one of the most diverse and unexplored ecosystems on the planet. The deep continental biosphere, the collective term for microbial life inhabiting deep crustal rock, fracture water, and hydrothermal systems far below the surface, is estimated to contain a biomass comparable to, and by some calculations exceeding, the total biomass of all surface life on Earth. That estimate carries enormous uncertainty, but the microbial communities themselves are not hypothetical. They have been sampled, cultured, sequenced, and characterized in mines, boreholes, and deep ocean drill cores. The organisms that populate the deep continental biosphere on Earth share several characteristics relevant to the Mars question. They are almost exclusively chemolithotrophic. They derive energy from inorganic chemical reactions, rather than from sunlight or organic compounds produced by photosynthesis. Their metabolic rates are extraordinarily slow by surface biosphere standards. Some communities appear to complete a single cell division cycle over timescales of thousands of years. Their water chemistry is ancient, isolated, and mineral-rich. Their environments are dark, pressurized, and anoxic, and they are present in the rock, in the water, in the fractures, everywhere that liquid water and chemical energy coexist at depth. If Mars ever produced life, and the planetary conditions during the Noachian and Hesperian periods were, by every chemical and physical metric, compatible with the requirements for life's origin, then the progressive retreat of liquid water from the surface to the subsurface over the past 3 to 4 billion years would have exerted precisely the kind of selective pressure that drives biological adaptation. An organism capable of surviving at diminishing water availability, retreating to deeper and deeper aquifer systems, tolerating increasing salinity and chemical stress, reducing its metabolic rate to match the declining energy availability of a cooling, desiccating world. Such an organism, if it ever existed, would have had billions of years to adapt to exactly the conditions that exist in the Martian mid-crust today. This is not a prediction. It is a mechanistic scenario grounded in the demonstrated responses of Earth's deep biosphere to analogous pressures over geological time. The evolutionary record of Earth's chemolithotrophs shows exactly this pattern: metabolic flexibility, tolerance of extreme conditions, and the capacity to sustain community viability at energy fluxes far below what any surface organism could survive. The deep biosphere does not need the sun. It does not need the surface. It needs rock, water, and chemistry. Mars has all three, at depth, right now. The methane signal at Gale Crater sits over a region of the Martian crust, whose subsurface structure, while not directly sampled, is geologically consistent with the water-bearing mid-crustal layer implied by the InSight seismic data. The seasonal pattern of the methane, rising in Martian summer, falling in winter, is consistent with thermally driven pressure changes in a subsurface gas reservoir, the kind of reservoir that could form above a water-bearing zone where biological or geochemical methane production was occurring at depth. The oxygen anomaly compounds that consistency. Two chemically distinct atmospheric signals, both seasonally periodic, both unexplained by known abiotic chemistry, both detected above the same crater, above the same crust. Coincidence remains a valid scientific concept. These signals may have independent abiotic explanations that simply have not yet been identified. The history of planetary science is full of apparent correlations that dissolved under scrutiny. The Viking lander biology experiments in 1976 initially returned results that appeared to indicate metabolic activity in the Martian soil, generating enormous excitement. Excitement that collapsed when subsequent analysis attributed the results to the chemistry of perchlorates and UV-oxidized soil compounds rather than biology. That lesson has never been forgotten in the Mars science community. But the Viking results were from the surface, in an environment exposed to ultraviolet radiation, perchlorate chemistry, and the full hostility of the Martian atmosphere. The signals being detected now point downward, into the protected, radiation-shielded, liquid water-bearing interior of a planet whose chemistry and thermal history have been progressively refined by 4 decades of increasingly sophisticated instrumentation. The question being asked today is not the same question Viking asked. It is deeper, in every sense of the word. The Perseverance rover is currently caching rock samples from Jezero crater in hermetically sealed titanium tubes, building a depot that a future sample return mission will retrieve and transport to Earth. Those samples will be analyzed with laboratory instruments, orders of magnitude more sensitive than anything that has yet operated on the Martian surface. Instruments capable of detecting individual organic molecules, isotopic biosignatures, and microbial morphological structures at the nanometer scale. The sample return architecture, though delayed and over budget, represents humanity's most direct near-term mechanism for asking the life question with the rigor that question deserves. The samples are waiting. The water is there. The chemistry is active. Mars is not silent because nothing is happening. Mars is silent because we have not yet built the instruments to hear what is being said. In the dark, under the rock, at the bottom of a column of ancient crust, in water that has been waiting for 1 billion years. On March 15, 2026, researchers at New York University Abu Dhabi published findings in the Journal of Geophysical Research. Planets confirming that ancient sand dunes in Gale Crater had been cemented into rock by groundwater moving beneath the Martian surface billions of years after the crater's surface lakes had completely disappeared. 2 days later, on March 17th, a separate analysis of RIMFAX radar data from the Perseverance rover revealed a buried ancient river system beneath the floor of Jezero Crater, a system far more extensive than anything visible from orbit, indicating that water had flowed across and beneath the Martian surface for a far longer period than any prior model had predicted. These findings were published within the same week, not the same decade, the same week. The cadence of discovery at Mars is accelerating. The instruments are older, the datasets are longer, and the analytical tools being applied to archived data are more sophisticated than anything that existed when the data was first collected. Mars is not revealing its secrets reluctantly. It is revealing them in the order that our instruments have become capable of reading them. And the order, as it turns out, points consistently in one direction: deeper, wetter, longer, and more chemically active than any prior consensus assumed. The timeline of Martian habitability, once drawn as a clean arc declining from a wet Noachian past to a frozen Amazonian present, has been revised into something far more complex and far more hopeful from an astrobiological standpoint. The work from Jezero Crater, published in January 2026 by a team led by Imperial College London, documented the first definitive physical traces of an ancient Martian shoreline. Wave-formed beach structures and rocks chemically altered by sustained subsurface water interaction preserved in the margin unit of the crater rim. The shoreline implies a standing body of water with sufficient surface area and longevity to generate wave action. The subsurface alteration implies that groundwater continued circulating through the crater floor long after the lake surface had evaporated. The habitability window at Jezero alone, one crater in one region on one planet, appears to have extended across multiple distinct phases of aqueous activity spanning hundreds of millions of years. What does that mean for the chemistry of life? On Earth, the origin of life, the transition from complex organic chemistry to self-replicating, metabolizing, enclosed biological systems, is estimated to have occurred approximately 3.8 to 4 billion years ago, within a few hundred million years of the planet's formation. The geological and geochemical conditions that enabled that transition are debated intensely. The leading hypotheses involve hydrothermal systems, either at mid-ocean ridges or in shallow surface pools with fluctuating wet-dry cycles, where concentration gradients and chemical energy gradients could drive the assembly of increasingly complex molecules. The timescale required, based on Earth's record, appears to be on the order of tens to hundreds of millions of years of stable aqueous chemistry. Mars had that. During the Noachian and into the Hesperian, stable liquid water systems, lakes, river networks, shallow seas, and hydrothermal environments persisted for hundreds of millions of years. The mineralogy is unambiguous. The clay-bearing terrains of the Noachian Southern Highlands record sustained water-rock interaction at low temperatures, the chemistry of a slowly evolving aqueous environment. The sulfate-bearing deposits of the Hesperian record a later phase of more acidic, mineral-rich water, chemically distinct from the earlier clays but still liquid, still reactive, still capable in principle of concentrating and preserving organic molecules. The organic molecules are there too. Curiosity confirmed the detection of complex organic compounds, chlorobenzene, dichloroalkanes, and thiophenic compounds, in 3-billion-year-old mudstone at Gale Crater in 2018. These molecules alone do not indicate biology. They could have been delivered by meteorites, synthesized by abiotic chemistry, or produced by both processes over geological time. But their survival in surface rock for 3 billion years, in an environment flooded with ultraviolet radiation and oxidizing perchlorate chemistry, tells us something important. The preservation potential of Mars is real. The planet is cold and dry, which means slow decay. Organics buried in ancient sediment, shielded from surface radiation by even a meter of rock, can persist across geological time. Whatever chemistry occurred in early Mars, biological or not, may have left a record. And that record is still there, waiting. The Perseverance sample cache represents the most direct attempt in the history of space exploration to bring that record to a laboratory on Earth. As of early 2026, the rover has sealed more than 20 sample tubes containing material from Jezero Crater's delta, floor, and margin units, material that spans multiple distinct geological episodes of aqueous activity. The Mars Sample Return Mission, the joint NASA-ESA architecture designed to retrieve those tubes and return them to Earth for analysis, has faced budget pressures and schedule delays that have pushed the earliest possible return date into the mid-2030s. The scientific community's frustration with those delays is proportional to its confidence in what the samples may contain. The analytical instruments waiting for those samples on Earth operate at a level of sensitivity that has no analog in any instrument ever flown to Mars. The NanoSIMS ion microprobe, used in terrestrial astrobiology laboratories, can map the isotopic composition of individual microfossils at spatial resolutions below 100 nanometers. Secondary ion mass spectrometry can detect organic biosignatures at concentrations of parts per trillion. Synchrotron X-ray tomography can reconstruct the three-dimensional internal structure of a rock sample at submicron resolution, revealing microbial morphological structures preserved in mineral matrices. If a microbial biosignature exists anywhere in the Jezero sediment samples, a carbon isotope fractionation pattern, a preserved cell wall, a coherent organic molecular assemblage with the structural characteristics of biological membrane lipids, these instruments will find it. That is not optimism. That is a statement about analytical capability grounded in decades of laboratory development, specifically motivated by the Mars question. The alternative outcome, the sample's return, every biosignature test is negative, and the organic compounds present are definitively abiotic in origin, is also scientifically valuable. A confirmed negative result from the best samples Mars has yet yielded would constrain the origin of life question in ways that are as profound, in their own way, as a positive detection. It would tell us that the chemical and physical conditions that enabled life on Earth, while present on Mars, were not sufficient to produce life there. That finding would push the origin of life toward either a uniquely Earth-specific mechanism, perhaps the Moon's tidal influence on early ocean chemistry, or some specific aspect of Earth's mantle composition, or the precise timing of the late heavy bombardment, or toward the conclusion that life's origin is genuinely rare in the universe, and that Earth is among a vanishingly small number of worlds where chemistry crossed the threshold into biology. Either answer changes our understanding of what we are and why we are here. Mars has been accompanying Earth on its orbit around the Sun for 4.5 billion years. The two planets formed from the same protoplanetary disk, accreted from the same population of rocky planetesimals, received the same initial inventory of water-bearing asteroids and organic-rich comets during the late heavy bombardment. For the first several hundred million years of solar system history, Earth and Mars were, in the broadest strokes, remarkably similar worlds. Rocky, water-bearing, volcanically active, chemically rich, and warmed by a young sun whose ultraviolet output was higher than today, driving photochemistry in both atmospheres. They diverged. Mars lost its magnetic field. Mars lost its atmosphere. Mars lost its surface water. The divergence was not caused by a catastrophic external event, but by internal physics. The smaller planet cooled faster, its iron core solidified sooner, and the loss of the magnetic dynamo exposed the atmosphere to the solar wind. The difference between Earth and Mars, in the end, may come down to a matter of mass. Earth is 10 times more massive than Mars. That extra mass meant more internal heat, retained longer, sufficient to sustain a liquid outer core and a magnetic field for 4.5 billion years. Mars, with 1/10 the mass, could not hold that heat. The magnetic field collapsed. The rest followed. 10 times the mass, separated by a gulf of time measured in billions of years. And yet the water is still there, underground in the dark, at 5 to 8 kilometers depth, in a volume that rivals the Arctic Ocean. The chemistry is still active. The methane still cycles with the Martian seasons. The ancient shorelines of Jezero are still readable in the rock. The river system buried beneath the crater floor was flowing, according to the RIMFAX data, more recently than any orbital imagery had suggested. Mars did not die cleanly. It retreated. It pulled its water underground, its heat inward, its chemistry deeper and slower and darker. Whether it pulled life along with it, whether anything was there to retreat, is the question that defines the next chapter of planetary science with a sharpness and an urgency that no prior generation of scientists has been able to feel, because no prior generation had the data to make the question this specific, this grounded, this close to answerable. The Viking landers touched down in 1976. For the 50 years since, Mars has been the subject of progressive, cumulative scientific interrogation conducted with instruments of increasing sophistication and missions of increasing ambition. Each one has found something the previous one missed. Each answer has opened a deeper question. The methane that Viking could not detect, the organic compounds that the first rovers could not confirm, the subglacial radar anomaly that required a decade of orbital passes to document, the seismic velocity anomaly that waited in InSight's data archive for 2 years after the lander fell silent before the right analysis extracted its meaning. The planet is still being read. The reading is still in progress. What the past year's discoveries have established, the shoreline at Jezero, the buried river system, the cemented dunes of Gale Crater, the seismic confirmation of a liquid water layer at depth, is that Mars remained a place where the chemistry of life was plausible, not for a brief window in the distant past, but across multiple extended phases of aqueous activity, stretching from the ancient Noachian surface all the way down to the present-day subsurface. That is the finding, not a single dramatic moment, not one instrument, one signal, one paper, a convergence, a body of evidence assembled over decades, from dozens of missions, by hundreds of scientists working on different continents with different instruments and different methodologies, arriving at the same conclusion from different directions. Mars was wet. Mars stayed wet, underground, for far longer than anyone modeled. Mars may still be wet, at depth right now. The next question is whether wet was ever enough. We do not yet know. The samples are sealed in their titanium tubes on the Martian surface, waiting for a vehicle that has not yet launched from Earth. The drill that could reach the mid-crustal aquifer does not yet exist. The seismometer that could characterize it in 3 dimensions has already gone silent in the dust. But the data is in the archive. The chemistry is in the rock. The water is in the dark. And the question, for the first time in the history of our species asking it, is no longer whether Mars could have harbored life. It is whether Mars still does.